Testing. Oh, okay, it's working. Hi, hello. Let me see. Oh, wow, 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 wow. Look who's here. Hello. I went and made coffee. That's why I was like, I need to wait 5 minutes. But look who's here. Hey, Coffee Cafe, how are you? Good morning, I think. Or maybe like good brunch time. Um, yes. Hi. Let's do this. Today is technically day 2 of this course that I have been taking. Hi, hi. I think I'll go like this for now and see if we'll need to use the other screen. I started this course on, yes, checking my sound. It's low, but it's there. All right, I'll put on GitHub NLP course. GitHub has a learning platform that I think I've put it in the chat, I think. Oh no, sorry, not chat. In the, all right, I'll put it in chat, but I think I put it in okay, in the description. There we go. That's the thing. So yeah, this does exist. There we go. And there's also this this.
Them for most of the things.
Shh. This course from Carnegie Mellon University called Advanced NLP that yesterday I watched half of lecture 1 and I found it really interesting because it was really interesting. So yeah, let's see how today goes, but that was yesterday. And I know this collab has fallen asleep, so I'm going to try and wake it up. Oh wait, that's the only thing we did. No, we did a bunch of stuff. I'll probably need to run everything again. I'll just say run before and let it have fun. I don't think I connected to GitHub. No. Yep, that's it. So yeah, I didn't do the setup part because I'm not doing it locally. I'm doing everything on Colab, but I was trying to do it locally for personal reasons, and I might do that offline. Oh god, okay. Oh no. There we go. Okay. So yeah, how do transformers work? Let me know if the text is readable or not, if I should zoom in more or not. Yeah. Your jacket is very cool, by the way. I do believe so. I stole it from something. There were 2 different jackets. This is one that I'm using, and I think it matches my headset. I guess it's steampunk. It's from some sort of event that was happening on Zulip. Normally these things are not for free, but because of the event I was able to snatch it. Thank you. Did I say Zulip? What is that even? The app that I'm using to do this. Zulip is like a Slack thing. It's ZEPETO. I say ZEPETO, like Geppetto, but I think that's wrong. So, how do transformers work? In this section, we will take a high level look at the architecture of transformer models. Okay. bit of history. Here are some reference points in the short history of transformer models. I think no, I didn't look at this, but I just quickly looked at this. So starting 2018, we have GPT, BERT, XLM, GPT-2, 1 year later, XLNet, Roberta, Albert, T5, BERT, Stillbert, Electra, GPT-3. That's when it all, that's when the Fire Nation attacked. DBERTA, Longformer, M2N100, Luke. Why Luke? So yes, this course was made in 2021. I don't know why they haven't updated it. It's 2024. But yeah. The transformer architecture was introduced in June 2017. Is that the paper? Attention is all you need. That's the paper. The focus of the original research was on translation tasks, so it's followed by the introduction of several influential models, including June 2018 GPT, the first pre-trained transformer model used for fine-tuning on various NLP tasks, and obtained the state-of-the-art research results. I don't think pre-trainer transformer model and then fine-tuning on various NLP tasks means transfer learning, right? I think they do sometimes do zero shot, but yeah. October, so we are looking at this here. BERT, another, that's 2018. Large pre-trained model, this one designed to produce better summaries of sentences. GPT-2, improved and bigger version of GPT that was not immediately, I remember that one. I remember it not being publicly. Do you hear this motorcycle? God, it's loud. Okay. I remember it's not being publicly available due to concerns by the CEO of X. At least that's what I remember. I don't remember knowing Sam Altman's name by then. Distillbert, a distilled version of birds that is 60% faster, 40% lighter. Whoa. Retains 97% of Bert's performance. BART and T5, they happen at the same time? Almost. Two large pre-trained models using the same architecture as the original transformer model. What does that mean? So what, they are using the same architecture? Same architecture as the original transformer model. These weren't? An even bigger version of GPT-2 that's able to perform well on a variety of tasks without the need for fine-tuning, called zero-shot learning. There we go. Okay. This list is far from comprehensive and is just meant to highlight a few of the different kinds of transformer models. Broadly, they can be grouped into three categories: GPT-like, BERT-like, and BART/T5. Okay, so GPT does autoregressive transformer models. Auto-encoding transformer models are BART-like, and BERT-like. So like original model has two halves. Oh yeah, encoder and decoder. And when some of the other ones used only one half. Yep, yep, yep. GPT is decoder only. BERT is encoder only. Ah, so okay, that makes sense. No worries, no. Uh, that is more, you explained it better because I didn't know what the regressive part meant, but that's decoder. And BERT is encoder, but this is sequence to sequence. Yeah, no, this talking about it like this didn't explain the same way you did. Thanks. I even have read it elsewhere, like saying something is encoder only, decoder only, or both, but I don't remember when. We'll dive into these more in depth later. Okay. By the way, just to keep this alive, there are some like no, not here, not here. Really, this is all explanation. I thought there was some points of like running. I thought we will find some code to run, but apparently not in this page. Trust me, on other pages there will be code. Don't worry. Even now, huh? There's an error? Why? So these are fine, but you are not. Oh, I used something. I used something from someone that didn't work. I should probably just remove this part because it's the same as no. I'm just gonna comment it out. I remember trying to find a model that I can just use from someone and it not working. Okay, you please continue because in case I might actually not need it, but in case I do, yeah. I mean, that summarization was not good. I mean, it was fine, but it wasn't good. And the translation, English to French to English, fine. English to Korean, very bad. Like, I didn't know it, like, even if I pause this and, like, saying, hello, my name is Ciel or something, and it would give you the weirdest thing. I don't know why this Helsinki NLP. I don't know. I mean, I don't know French, so I can't judge it, but yeah. They're not perfect, but it's fine. It's fine. Okay. Transformers are language models. Okay. Mm, all the transformer models mentioned above have been trained as language models. Okay. This means they have been trained on a large amount of raw text in a self-supervised fashion. Self-supervised learning is a type of training in which the objective is automatically computed from the inputs of the model. That means that humans are not needed to label the data. Woohoo! This is fun. Um, but it's good if there is labeled data. It's always better. Um, this type of model develops a statistical understanding of the language it has been trained on, but because of the word embeddings or encoding thing, it's not very useful for specific practical tasks. Because of this, the general pre-trained model then goes through a process called transfer learning. Okay. During this process, the model is fine-tuned in a supervised way that is using human annotated. So we have a base model and then you teach it other stuff on a given task by fine-tuning it. Aha. That makes sense. Okay. An example of a task that is predicting the next word in a sentence having read the n previous words is called casual language modeling because the output depends on the past and present inputs, but not future ones. Is this like saying, like this is not generation? Or is this like a context window? Anyway, okay, is that an example? My name should come next. This is a window. I think he was talking about this yesterday. That's why my brain is like, alright. I think he was. Or was it not him? Was it me watching a video from Andre Karpathy? Which is actually this video that I have
I'd like to keep this
opened. Okay, anyway. My name, yeah, got it. Another example is masked language modeling, which we saw here, that you can mask something and ask it to predict it. Causal. Haha. Oh my god. Causal, not casual. Is this the second time me making this mistake? It is very confusing. Causal, you're right. It's coming. I think it is the second time I'm making this mistake and you pointing it out, so thank you. I was like, why is it casual? It's not about like normal human speech. But causal and predicting, that makes sense. So, thank you. I would have just continued without noticing. Alright. Yes, the masking part is a thing that exists, which is pretty cool. Transformers are big models. I don't know why this feels like I'm reading child book. Like, yeah, okay. Transformers are language models. Transformers are big models. Apart from a few outliers like Distilbert, because it's smaller, the general strategy to achieve better performance is by increasing the model size, as well as the amount of data they are pre-trained on. Distilbert is down here. Is it created by Carnegie Mellon University? Huh. Or is XLNet by Carnegie Mellon? Oh, Distilbert is by HuggingFace. That's cool. Elmo is by Allen Institute, I think. BERT is by Google, Microsoft, Facebook, another university. Ooh, fancy. And NVIDIA. Whoa, that's big. But I'm curious about number of parameters. Should we check? LLMs and like LLM graph, like number of parameters, something. Does such a thing exist? I need some visualization. Oh. Interesting mix of assumed knowledge between explaining model is big here versus saying model is autoregressive without. Yeah, Elmo, Bart, Grover, the other ladder IO, haven't heard of, from Sesame Street. Model naming, yeah. They love Sesame Street characters. I don't think I know Grover, but what else is there? Mina, that's a fun name. Bart is from Simpsons. We have here until 2023. We have Llama. Look at okay, GPT-3 versus Llama. Okay, that is comparison I can get behind. Publication date. This is updated. No, it's not. We have GPT-4 comparing it to GPT-3 or comparing it. Llama 2 is doing well, like saying the parameters not being too big and being newer than GPT-4. Huh. Like, look at the parameters being almost the same. Cool stuff. Okay, I'm gonna go back. Bart is Bert variant. Okay, Bart is Bert. Two very, very different characters. Um, we should have Big Bart, as in Big Bert. But yeah, Bert is from Google, Bart is from Facebook. Roberta, I'm just saying naming wise. Um, Unfortunately, training a model, especially a large one, requires a large amount of data. This becomes very costly in terms of time and compute resources. It even translates to environmental impact. That is very, very true. As can be seen in the following graph. I'm gonna zoom in a bit more. Okay, so round trip flight New York to San Francisco. That's carbon emissions. Yep, CO2 emissions. Human. I mean, that is okay. See that's what I was about to say. What is an average human life if in a place like New York? Then it's saying U.S. Okay, that's fair. And then state of the art LM training uh, with 200 billion parameters. That's very, very US car including fuel. One car? Okay, it's basically like driving. And is this like one time? Because these are all lifetime. That's scary. I know this was a discussion point. Um, Very not fun. Ooh, about carbon emissions.
So let's talk about the carbon footprint of transformers. Maybe you've seen headlines such as this one that training a single AI model can emit as much carbon as 5 cars in their lifetimes. So, when is this true and is it always true? Well, it actually depends on several things. Most importantly, it depends on the type of energy you're using. If you're using renewable energy, such as solar, wind, hydroelectricity, you're really not emitting any carbon at all, or very, very little. If you're using non-renewable energy sources, such as coal, then their carbon footprint is a lot higher because essentially you're emitting a lot of greenhouse gases. Another aspect is training time. So the longer you train, the more energy you use. The more carbon you emit, right? So this really adds up, especially if you're training large models for hours and days and weeks. The hardware you use also matters because some GPUs, for example, are more efficient than others, and utilizing.
Mm, did her graphics say 200 million parameters instead of billion? Um, I don't know because it was B here. I can zoom in. Should I go back? I don't remember her sharing any graphics. Oh, here. Oh, okay. This one says million, but the numbers are very different, right? 75. Yeah. This here 53, this here 75, this here. This number is very different. Why? Because US car. This is also US car. Why are the numbers so different? 53, 152. That is bigger. Okay, let's assume it's a bigger car. I don't know. But this number here is so... am I losing sight? This is only 75,000, while this is 600,000. And it's million. Neural architecture. This here is saying... the numbers are so different. Yeah, for billion it's very low compared to this being million. Alright.
Energy you use, the more energy you use, the more carbon you emit, right? So this really adds up, especially if you're training large models for hours and days and weeks. The hardware you use also matters.
Like we wouldn't stress about 1.5 cars worth. I mean, you can stress about anything if you set your mind to it. I'm really good at stressing.
Because some GPUs, for example, are more efficient than others and utilize...
I mean, obviously, no, they don't. A big company doesn't care about a car worth of things. And you're right, this here is 1 point, yeah, something. But it was brought up in a lot of I don't know, like 2020s or like 21. I don't remember, but it was on Twitter saying how much it costs to train models, and it was more social pressure because a company, like whatever company, doesn't really care about this unless people make them care about it, right?
Efficient GPUs properly, so using them 100% all the time, can really reduce the energy consumption that you have, and then once again, reduce your carbon footprint. There's also other aspects such as I/O, such as data, etc., but these are the main three that you should focus on. So when I talk about energy sources and carbon intensity, what does that really mean? So if you look at the top of the screen, you have a carbon footprint of a cloud computing instance in Mumbai, India, which emits 920 grams of CO2 per kilowatt hour. This is almost 1 kilogram of CO2 per kilowatt hour of electricity used. If you compare that with Canada,
Why?
Montreal, where I am right now, 20 grams of CO2 per kilowatt hour. So that's a really, really big difference, almost more than 40 times more carbon emitted in Mumbai versus Montreal. And so this can really, really add up if you're training a model for weeks, for example.
Is it like about the fuel that's being used? Carbon emissions can vary up to a factor of 40 depending on the grid's energy mix. Because like we use oil. I mean, I personally don't use oil. Maybe I use it half of the time because we have solar panels, but yeah.
For example, you're multiplying times 40 the carbon that you're emitting. So choosing the right instance, choosing a low carbon compute instance is really the most impactful thing that you can do. And this is where it can really add up if you're training in a very intensive, in a very carbon intensive region.
I have a question. Would like when getting virtual servers and stuff ready for training a model, do they tell you how much, like, is it something you can choose? how much emission there will be. Data center uses. Oh, I saw a stat that a chat with ChatGPT so use half a liter of drinking water. Ah, no way. How long? Don't tell me just one. That is very easy to visualize and like be disturbed by. Whoa. I'm rethinking things now.
Other elements to consider, for example, using pre-trained models. That's the machine learning equivalent of recycling. When you have pre-trained models available, using them, you're not emitting any carbon at all, right? You're not retraining anything. So that's also doing your homework and kind of looking around what already exists.
That's a good point. They might have an option for carbon offsets. But you have to be careful. Some of the cheapest carbon offsets aren't real. I know, you're right. I saw the video by John Oliver about companies greenwashing. I think it was from John Oliver. I think Shell. Shell? What's Shell? Just go in trouble for selling bogus carbon credits. Okay. They got in trouble? Yeah, yeah, yeah. I've heard some of this stuff, yeah. Major petroleum company. I know some of the names of the petroleum companies, but not that one. I guess they don't work in Iraq. Anyway.
Fine-tuning instead of training from scratch. So once again, if you find a model that is almost what you need but not quite, fine-tuning the last couple of layers, making it really fit your purpose instead of training a large transformer from scratch can really help. Starting with smaller experiments and debugging as you go. So that means, for example, figuring out data encoding, figuring out...
I think it's Exxon Mobil, I think. I don't know. I have no idea slash don't care because it doesn't matter. I don't know.
Making sure that there's no small bugs that you'll realize, 16 hours into training. Starting small and really making sure that what you're doing, what your code is stable. And then finally, doing a literature review to choose hyperparameter ranges, and then following up with a random search instead of a grid search. So random searches for hyperparameters combinations have actually shown to be as efficient in finding the optimal configuration as grid search. But obviously you're not trying all possible combinations, you're only trying a subset of them. So this can really help as well. So now if we go back to the original paper by Strubel et al. In 2019, the infamous 5 cars in their lifetimes paper, if you just look at a transformer, a 200 million parameter transformer, its carbon footprint is around 200 pounds of CO2, which is significant, but it's nowhere near 5 cars, right? It's not even a transatlantic flight. How it really adds up is when you're doing neural architecture search, when you're doing hyperparameter tuning, and this is trying all possible combinations, et cetera, and this is where like the 600,000 pounds of CO2 came from. So this is really where things add up. So, but if you're doing things mindfully,
that makes more sense in a way. It has more explanations about the carbon footprint. Same thing, but different usage.
And conscientiously, then your carbon footprint won't be as big as the paper implied. Some tools to figure out how much CO2 you're emitting. There's a web-based tool called the Machine Learning's Emissions Calculator, which allows you to manually input, for example, which hardware you used, how many hours you used it for, where it was located, locally or in the cloud, and then it's going to give you an estimate of how much CO2 you emitted. Another tool that does this programmatically is called Code Carbon. So you can pip install it. You can go to the GitHub, and essentially it runs in parallel to your code. So essentially you call it, and then you do all your training, and then at the end It's going to give you an estimate, a CSV file with an estimate of your emissions, and it's going to give you some comparisons. It's got a visual UI where you can really look at how this compares to driving a car or watching TV. So it can give you an idea of the scope of your emissions as well. And actually, Code Carbon is already integrated into Auto NLP, and hopefully people will be using it out of the box and easily tracking their emissions all through training and deploying transformers.
I am happy that these things exist, but also do not blame the everyday people when there are companies that are the equivalent of billions of people. Okay? I am very unhappy about this. Anyway, this is showing a project for a very big model led by a team what is concisely? Nope. Yes, okay. Trying to reduce the environmental impact of pre-training the footprint. Why are we starting with the word and? Okay, from this graph, okay. Of running lots of trials to get the best heart. That's what makes it like big. Doing too many tests on a lot of data. Okay. Imagine if each time a research team, a student organization, or a company wanted to train a model, did it from scratch. This would lead to huge unnecessary. There's a motorcycle passing. Oh, hi, hi. Hello. How are we doing? We are currently worrying about carbon emissions of language models. So, not the best. Could be better. Overall, health is good. What about you? How are you doing? Thank you for passing by. This is why sharing language models is paramount. Sharing the trained weights and building on already existing, already trained weights reduce the overall compute cost and carbon footprint of the community. And I don't mind the fact that this is blaming, like bringing to light, because almost all LLMs are, or just any language model, is coming from big companies and maybe a university here and there. So I don't mind this part. I just mind it when they're blaming the everyday people. By the way, you can evaluate the carbon footprint of your models training through these tools that we looked at. Perhaps a good argument for open source foundation models so companies don't have to start from scratch. Yeah, that's a really good argument. And that was a point that was raised in this video, saying use pre-trained models, fine-tune models, start with test data and not do everything. So these are really good points. We were also talking about greenwashing, which is a thing. Is the voice like difference too much? Let me know so that I can fix it. Because that whoosh was really loud. Let's see.
What is transfer learning? The idea of transfer learning is to leverage the knowledge acquired by a model trained with lots of data on another task. The model A will be trained specifically for task A. Now let's say you want to train model B for a different task. One option would be to train the model from scratch.
Yeah, I know the other day was really bad, so sorry about that. Sounds like companies like OpenAI are pushing for the US to advocate for closed models. No. I mean, didn't they start with ChatGPT 2 saying the, people shouldn't have access to this because it's too powerful? Or is it something new that I have not heard of?
This could take lots of computation, time, and data. Instead, we could initialize model B with the same weights as model A, transferring the knowledge of model A on task B. When training from scratch, all the model's weights are initialized randomly. In this example, we are training a BERT model on the task of recognizing if two sentences are similar or not. On the left, it's trained from scratch, and on the right, it's fine-tuning a pre-trained model. As we can see, using transfer learning on the pre-trained model yields better results. And it doesn't matter if you train longer. The training from scratch is capped around 70% accuracy, while the pre-trained model beats the 86% easily. This is because pre-trained models are usually trained on large amounts of data that provides the model with a statistical understanding of the language used during pre-training. In computer vision, transfer learning has been applied successfully for almost 10 years. Models are frequently pre-trained on ImageNet, a dataset containing 1.2 million of photo images. Each image is classified by one of 1,000 labels. Training like this, on labeled data, is called supervised learning. In natural language processing, transfer learning is a bit more recent. A key difference with ImageNet is that the training is usually self-supervised, which means it doesn't require human annotation for the labels. A very common pre-training objective is to guess the next word in a sentence, which only requires lots and lots of text.
Right.
GPT-2, for instance, was pre-trained this way using the content of 45 million links posted by users on Reddit. Another example of
Why Reddit? It's my favorite place to go, but it doesn't have the best words.
Self-supervised pre-training objective is to predict the value of randomly masked words, which is similar to fill-in-the-blank tests you may have done in school.
Yeah.
BERT was pre-trained this way using the English Wikipedia and 11,000 unpublished books.
Cool.
In practice, transfer learning is applied on a given model.
What does unpublished books mean? That's interesting. Unpublished books.
By throwing away its head. That is,
didn't use Reddit, but rather you're right. He did say links. That's a cool idea to make it credible. Or just a place that people put links. Like go to Today I Learned and you'll see a lot of fun stuff.
Its last layers focus on the pre-training objective and replacing it with a new, randomly initialized head suitable for the task at hand. For instance, when we fine-tuned the BERT model earlier, we removed the head that classified masked words and replaced it with a classifier with two outputs, since our task had two labels.
Yeah. Trick people used. That's what I thought of. The Google has been ruined by SEOs and advertising. Oh yeah. Okay. Nope, that's not what I thought of. People using Reddit like a search engine. Yeah, I guess when you want a real answer to a question, you ask the question and say Reddit. But what I was thinking about is how, I am back. Okay, how Google started. It was basically how many times a website was linked to that would put you to the top. I think.
To be as efficient as possible, the pre-trained model used should be as similar as possible to the task it's fine-tuned on. For instance, if the problem is to classify German sentences, it's best to use a German pre-trained model.
Right.
But with the good comes the bad. The pre-trained model does not only transfer its knowledge, but also any bias it may contain. ImageNet mostly contains images coming from the United States and Western Europe. The models fine-tuned with it usually will perform better on images from these countries. OpenAI also studied the bias in the prediction of its GPT-3 model, which was pre-trained using the
PageRank named after Larry Page. Really? So it doesn't have anything to do with actual pages? Okay.
Guess the next word objective. Changing the gender of the prompt from he was very to she was very changed the predictions from mostly neutral objectives to almost only physical ones. In the model card of the GPT-2 model, OpenAI also acknowledges its bias and discourages its use in systems that interact with humans.
Okay, yeah. That was just really loud. Language models are biased because people are biased. Happy accident of, yeah. Happy accidents. Happy trees and happy accidents. Pre-training is the act of training a model from scratch. The weights are randomly initialized and the training starts without any prior knowledge. But you're still, yeah, training. Okay. We have a base model, a large corpus, we do training, we give it money, and then the model is pre-trained. Woohoo! Okay. This page is so long. I'm tired. I wanna. How much longer? Am I only halfway? Why? Oh God. Oh no. Actually, it's not that bad. Okay. It's fine. It's okay. Let's see. Cause I think yeah. Nope. It's really halfway. It's alright. Wait. When I finish this, I'm gonna go to the video because I am tired of reading. My eyes. My eyes. Yeah. Pre-training is usually done. I need to change the scene. Okay. On a very large amount of data, therefore it requires a very large corpus of data, and training can take up several weeks. No. Oh my God. Fine-tuning on the other hand, okay. Is training is the training done after model has been pre-trained to perform. Oh, pre-training is making the base. Okay. To perform fine-tuning, you first acquire a pre-trained language model, then perform additional training with a data set specific to your tasks. Wait, why not simply train the model for your final case from scratch? There are a couple of reasons. Let's look at the reasons. The pre-trained model was already trained on a dataset that has some similarities with the fine-tuning dataset. The fine-tuning process is thus able to take advantage of knowledge acquired by the initial model. During pre-training, for instance, with NLP problems, the pre-trained model will have some kind of statistical understanding of the language you are using for your task. Not always. I don't think I can find many pre-trained languages models for languages around here. Since the pre-trained model was already trained on lots of data, the fine-tuning requires way less data to get decent results. For the same reason, the amount of time and resources needed to get good results are much lower. Cool. For example, one could leverage a pre-trained model on the English language and then fine-tune it on an archive corpus, resulting in a science research-based model. The fine-tuning will only require a limited amount of data. The knowledge the pre-trained model has acquired is transferred, hence the term transfer learning. Okay. So we have a pre-trained language model. We train single GPU. That's cool. Easily reproducible. Really? Oh. And then we give it money because everything works with money. I think with language, one might hope that knowledge of the same other languages might transfer to a new language. Yeah, sort of. But you have some issues like tokenization not being ideal. I think my main issue is with Anglo stuff. I don't know. I mean, I haven't done research, but how good is an English language model for something Arabic? Maybe not that bad, because I've been focusing on ASR a bit, trying to test some stuff, not going anywhere far, but if the new language doesn't have as much text, to train over the base languages can give base language can give it a lot of like common sense knowledge and total fair. Still it's useful. Like it's always useful to not start from zero, I think. But being very different languages could cause issues. From what I know, there are good results. I don't know if there has been any testing on transformer models, but I know there was something on Hugging Face that I tested, and it was like decent, and I was just testing it myself with no like metrics. I was the metric. Yep. Fine tuning a model therefore has lower time, data, financial, and environmental costs. It is also quicker and easier to iterate over different fine-tuning schemes, as the training is less constraining than a full pre-training. This process will also achieve better results than training from scratch unless you have lots of data, which is why you should always try to leverage a pre-trained model, one as close as possible to the task you have at hand, and fine-tune it. And based on the task that you're doing, the model will be better if it's pre-trained, even if it's not on the same language, but it's on the task, I think. Especially thinking ASR, because audio is audio, even if the vocabulary is different. I'd like to think that. General architecture. In this section, we'll go over general architecture of the transfer model. Don't worry if you don't understand some of the concepts. There are detailed sections later covering each component. Yes. Was I trying to fine-tune Whisper? I think that was like a month ago when I was trying to fine-tune Whisper. There is a really nice blog about it. I kept failing. I think it was because Colab didn't have enough, the free version, didn't have enough compute power. So I never got there, but now I might have access to some resources, and I'm not trying Whisper this time. I'm trying Wave2Vec. I think that's the one by Meta, Facebook. And if that goes well, I might jump to Whisper. So if you are willing to help me, I am. But there are really nice blog posts. I just need to set up the environment first. And I don't know what I need exactly, so we'll see. Yeah. But I also like learning about general information, especially on transformers, so that I know more.
Let's study the transformer architecture. This video is the introductory video to the encoders, decoders, and encoder-decoder series of videos. In this series, we'll try to understand what makes a transformer network, and we'll try to explain it in simple, high-level terms. No advanced understanding of neural networks.
Haha. Yeah, an idiot. Astaghfirullah. That can answer every question. Okay, cool. Thank you.
Is necessary, but an understanding of basic vectors and tensors may help. To get started, we'll take up this diagram from the original Transformer paper entitled Attention is All You Need by Vaswani et al. As we'll see here, we can leverage only some parts of it according to what we're trying to do. We won't dive into the specific layers building up that architecture, but we'll try to understand the different ways this architecture can be used. Let's first start by splitting that architecture into two parts. On the left, we have the encoder, and on the right, the decoder. These two can be used together, but they can also be used independently. Let's understand how these work. The encoder accepts inputs that represent text. It converts this text, these words, into numerical representations. These numerical representations can also be called embeddings or features. We'll see that it uses the self-attention mechanism as its main component. And we recommend you check out the video on encoders specifically to understand what is this numerical representation, as well as how it works. We'll study the self-attention mechanism in more detail, as well as its bidirectional properties. The decoder is similar to the encoder. It can also accept text inputs. It uses a similar mechanism as the encoder, which is the masked self-attention as well. It differs from the encoder due to its unidirectional feature, and is traditionally used in an autoregressive manner. Here too, we recommend you check out the video on decoders especially to understand how all of this works. Combining the two parts results in what is known as an encoder-decoder, or a sequence-to-sequence transformer. The encoder accepts inputs and computes a high-level representation of those inputs. These outputs are then passed to the decoder. The decoder uses the encoder's outputs alongside other inputs to generate a prediction. It then predicts an output, which it will reuse in future iterations, hence the term autoregressive. Finally, to get an understanding of encoders-decoders as a whole, we recommend you check out the video on encoder-decoders.
Okay, that was precise and useful. Thank you. All right. The model is primarily composed of two blocks, encoder and decoder. Encoder is the first one. Receives input, builds a representation of its features. This means that the model is optimized to acquire understanding from the input. And then the decoder uses the encoder's representation, the features, along with other inputs to generate a target sequence. This means that the model is optimized for generating output. Cool. Okay, these are the things that we were talking about. Each of these parts can be used independently depending on the task. Encoder-only models, good for tasks that I think classification is, require understanding of the inputs such as sentence classification and named entity recognition. Decoder-only models, good for generative tasks. Such as text. That's why GPT was decoder-only, right? Encoder-decoder or sequence-to-sequence models, good for generative tasks that require input, such as translation or summarization. I think ASR are also sequence-to-sequence because it's the same idea of translation. I think. Might be wrong. We will dive into these later. Got it. Attention layers. A key feature of transformer models is that they are built with special layers called attention layers. In fact, the title of the paper introducing the transformer architecture. Something distracted me. Okay. Attention is all you need. It's a good title. It is a attention-grabbing title. We will explore the details of the attention layer. God knows how many times it's been cited. Congratulations to the authors, honestly. We will explore the details of the attention layer later in the course. For now, all you need to know is that this layer will tell the model to pay specific attention to certain words in the sentence you passed and more or less ignore the others when dealing with the representation of each word. To put this into context, consider the task of translating text from English to French. Why? Given the input you like this course. A translation model will need to also attend to the adjacent word you to get the proper translation of the word like, because in French the verb like is conjugated differently depending on the subject. Interesting. I got distracted by this person trying to run an ad on my chat, so I am going to say no, let's not do that. How do I do that? Okay, apparently I don't know how to do that. Oh well. Nope. I can either pin it or reply to it, which is none of the things that I want to do. Huh. I don't want to block them. I don't know how bad they are. Okay. I guess I can block them. Oh yeah, you're right. Okay. Thank you. Would Okay, I don't know if I am. I'm afraid if I put it in chat, would it happen? Speaking of French phrases like sound like, oh my god, yes, I saw that somewhere. Yes. And I think people on the news were reading it. I'm gonna try the ban thing and see if it works. If it doesn't, that is not going to be fun. But let me copy their name so that I don't write it wrongly. Huh, user I'm trying to ban doesn't exist. Huh? What? Yeah, no, you're right. It is /ban. You gave me the right information. And then okay, I'm gonna try one more time. Oh, huh. Oh, that's really sweet. Okay. I doubt it would take one person. Thanks. All right. I'm going back into this part and change the scene so that it can be seen better. Is it? I have no idea. Alright. Changing scene. Before I change scene, I do need to check. There we go. Checked. There. Okay. Got it. Alright. So we were saying French is like Arabic where you have to be careful. No? Maybe not, actually. Anyway, stuff happens with the words. The rest of the sentence, however, is not useful for the translation of that word. In the same vein, when translating this, the model will also need to pay attention to the word course, because this translates differently depending on whether it's masculine or feminine. That's what I was about to say. It's the same in Arabic. I think. Is it this? Anyway. Again, the other words in the sentence will not matter for the translation, of course. With more complex sentences and more complex grammar rules, the model will need to pay special attention to words that might appear further away. Yeah. Singular, plural, far, near, wherever they are. The same concept applies to any task associated with natural language. Word by itself has a meaning, but that meaning is deeply affected by the context, which can be any other word or words before or after the word being studied. How would it know to pay attention? I'm curious about that. Now that you have an idea of the attention layer, what attention layers are all about, let's take a closer look at the transformer architecture. How much longer do we have? Not much? Much. Okay. The original architecture. Let me zoom in. Zoom. That's good. Hopefully readable. It learns the amount of attention. Okay. I guess with some sort of feedback. I don't think it's reinforcement style, but let's see. Transformer architecture was originally designed for translation. During training, the encoder receives inputs, sentences, in a certain language, while the decoder receives the same sentence in the desired target language? Really? That's cheating. I didn't know that. In the encoder, the attention layer can use all the words in a sentence. Since we just saw, the translation of a given word can be dependent on what is before or after. Yep. The decoder, however, works sequentially and can only pay attention to the words in the sentence that it has already translated. No, it hasn't translated. Hold up. The decoder receives it in the target language. It's not translated it, has it? So only the words before the word currently being generated. For example, when we have predicted the first three words of the translated target, we give them to the decoder, which then uses all the inputs of the encoder. Okay, I need to read that again. When we have predicted the first three words of the translated target, we give them to the decoder, which then uses all the inputs of the encoder to try and predict the fourth word. The first three were done by who or what? Decoder? Encoder? There has been some work critical of the degree of teacher forcing for not training models to think ahead very well. Okay. We want them to think ahead, right? To speed things up during training, when the model has access to target sentences, the decoder is fed the whole target, but it is not allowed to use future words. If it had access to the words at position 2 and it was trying to predict 2, yeah, then it would just put it there. The problem would not be very hard. That makes sense. Yeah, maybe it was a bit cryptic, but not in a bad way. For instance, when trying to predict the fourth word, the attention would have access to the first three. Okay, now that makes sense. The original transformer architecture looks like this, with the encoder left, decoder right. We have the input, we have it being embedded, right? Word embeddings, and then multi-head attention, add and normalize, feed forward, add and normalize. This gets the output. Shifted right as in it doesn't get the current thing, I think. So is the masking of the current thing to be? And then this goes here. And then that. And then a linear layer and a softmax layer. Okay. Note that the first attention layer in a decoder block pays attention to all past inputs of the decoder, but the second uses the output of the encoder. We saw that here. First, second gets this. Teacher forcing. Think next word prediction. When the model makes a wrong prediction for the previous word, you change its answer to the gold standard text for the new next word. Very good for the cosm mask for training in parallel. Yeah. Okay. And you have to like tell the model you're wrong, right? Maybe? Where was I? First, thus it can thus access the whole input sentence to best predict the current word. This is very useful as different languages can have grammatical rules that put the... Oh god, that scared me. Okay, I don't care. Put it away. Okay. This is very useful as different languages can have grammatical rules that predict word. Or some context provided later in the sentence may be helpful to determine the best translation of a given word. So you update the weights. Okay, yeah, that makes sense. For each wrong answer, but it might be argued that the model never learns to recover. Oh, that's so sad for making a mistake. That's really sad. So you have to have a recovery layer. The attention mask can also be used in the encoder decoder to prevent the model from, paying attention to some special words. For instance, the special padding used to make all the inputs same length when we do that. Yes, we do that. Architecture versus checkpoints. Why are checkpoints being versus to architecture? As we dive into transformer models in this course, you will see mentions of architecture and checkpoints as well as models. Yeah. Okay, just telling us what they are. These terms have different meanings, obviously. Architecture is the skeleton of the model. The definition of each layer and each operation that happens within the model. Checkpoints, these are the weights that will be... Oh, okay. Aren't checkpoints supposed to be... So you update the weights independently for each wrong answer, but it might be argued that... Wait, why am I reading this again? Sorry. I thought it was a new chat. Checkpoints are like an update, a trained thing, aren't they? Model is an umbrella term, isn't as precise as architecture or checkpoint. It can mean both. This course will specify architecture or checkpoint when it to reduce ambiguity. Checkpoint is supposed to mean, maybe they mean, it might be confused. Yeah. You can load different checkpoints of trained models, right? For example, BERT is an architecture, while is a set of weights trained by Google team for the first release of BERT is a checkpoint. However, one can say the BERT model and this model. Cool. Very, very cool. Yes, they made it confusing. You can just say what they are. And now that I just went through this long... Why did it feel so long? I am not going to go to the next part, even though look how short it is. I am going to go here. I don't know, like maybe the next 15, 20 minutes. Let's see how much time I can have. We were, yeah. Should I go back or forward? Yes. Okay, here. Actually, maybe here. Let me go forward a bit more. Okay. That's where we are. So, in this lecture, here are the slides, I think. Yep. I can also put this somewhere because BERT is an architecture, whatever would be the model. Is for like Latin. Oh, all lower because tokenizing. Yeah, it's a model. It's the model, but at a checkpoint. Especially if it's like the latest version, then it's the model. So now that's where I am. I put this link in the chat of this page. One can go to the lectures. I mean, it's on YouTube, obviously. And go to this one that we were at. I opened the slides. And then how did you know I was there last time? And yeah, he does yep. Where's the thing with the rule-based? Yeah, so he tried making a rule-based NLP system. If you find this word, say it's positive or negative, and then next part is using ML. Let's see.
So next is machine learning based NLP.
The way that I paused it at him saying, so next is machine learning. Wow.
And machine learning in general, here actually when I say machine learning, I'm going to be talking about the traditional fine-tuning approach where we have a training set, dev set, test set. And so we take our training set, we run some learning algorithm over it. We have a learned feature extractor F, possibly learned feature extractor F, possibly learned scoring function W. And then we apply our inference algorithm, our decision rule, and make decisions. when I say possibly learned, actually the first example I'm going to give of a machine learning-based technique is doesn't have a learned feature extractor, but most things that we use nowadays do have learned feature extractors. So our first attempt is going to be a bag of words model. And the way a bag of words model works is essentially we start out by looking up a vector where one element in the vector is 1 and all of the other elements in the vector are 0. And so if the word is different, the position in the vector that's 1 will be different. We add all of these together, and this gives us a vector where each element is the frequency of that word in the vector. And then we multiply that by weights, and we get a score. And here, as I said, this is not a learned feature vector. This is basically, sorry, not a learned feature extractor. This is basically a fixed feature extractor, but the weights themselves are learned. So my question is, I mentioned a whole lot of problems before. I mentioned infrequent words. I mentioned conjugation. I mentioned different languages. I mentioned syntax and metaphor. So which of these do we think would be fixed by this sort of learning-based approach? Any ideas?
Yeah, Jeremy Howard talked about this in an Excel sheet, and he created the probability part. Yeah, I remember it in my head, which makes it easier.
Maybe not fixed, maybe made significantly better.
What issue does this fix? Understanding?
Any brave
Any brave souls want to volunteer as tribute?
Maybe negation? Okay, so maybe doesn't when you had a negative quote, yeah. Yeah, so for the conjugation, if we had a conjugations of the stems mapped to the same position, that might fix the conjugation problem. But I would say if you don't do that, then this kind of fixes conjugation a little bit, but maybe not really. Yeah.
He should repeat that. I am hearing nothing.
Yeah, if it's a big enough training set, you might have.
I think they're also looking at the same data set, movie reviews. Oh yeah. Yesterday there was a part where he was looking at movie reviews that were so like saying this movie didn't make me throw up, which is like, it's positive. So I mean, like, it didn't make me hate myself, sort of thing.
Have covered the various conjugations, but if you haven't and you don't have any rule-based processing, it might still be problems. Yeah. Yeah. So infrequent words, if you have a large enough training set, yeah, you'll be able to fix it to some extent. So none of the problems are entirely fixed, but a lot of them are made better. Different languages is also made better if you have training data in that language, but if you don't, then you're out. So
the issue of the rule-based being things are not updated, that part?
So now what I'd like to
Lol, indeed.
do is I'd like to look at what our vectors represent. So basically, in binary classification, each word, so the vectors themselves represent the counts of the words. Here I'm talking about what the weight vectors or matrices correspond to. And the weight vector here will be positive if the word, it tends to be positive if in a binary classification case. In a multi-class classification case, we'll actually have a matrix that looks like this.
But these are learned, right? Okay, got it.
Where each column or row corresponds to the word, and each row or column corresponds to a label. And it will be higher if that row tends to correlate with that. That word tends to correlate with that label. So this training of the bag of words model can be done so simply that we can put it in a single slide. So basically here, what we do is we start out with the feature weights.
Okay.
And
yeah. This is cute anecdote like with GPT. Requiring a review of a label data set for sentiment as it was more sensitive to sarcasm. Haha! Than some of the human labelers, which was really surprising. Wow! So it could sense sarcasm more then I mean, sarcasm can go over your head, especially if it's not your main language. Things are very context dependent. That's a really cool fact.
And for each example in our data set, we extract features.
I imagine human labelers don't spend too much time thinking about the task. They get bored and get distracted. That's very true. Yeah, I get distracted way too much. That's a really bad example, but I'm listening to I'm making air quotes an audiobook from the book Red Rising, but like book 2, and like this has nothing to do with this, and don't want to do spoilers, but the guy is like, how did I lose focus of my mission? And I'm like, yeah, for this year I have something to do, like I have a mission for this year, and the way that I keep I continuously procrastinate and lose sight of my mission. Yeah, I'm human and I get distracted. So, yes.
And for each example in our data set, we extract features. The exact way
Oh, I just thought of something. Next generation of CAPTCHA would be how fast we get distracted. Bad, but still. Yeah. Like showing some videos, informational videos, and you're like skip, and then of course that's a human. And then models can learn from us happily.
Extracting features is basically splitting.
As long as you don't spoil Pantheon? Hey! Okay. Oh wow, I had forgotten that I recommended the series Pantheon. No way. It's fun, and somewhat heavy at points. Like some of the human stories are very heavy. Yeah, I had a hard time getting into Red Rising. I tried reading it, I think, one time before, but the first like chapter is interesting, but it was like, oh, that's intense and like not going anywhere. And then now, book 1 was a roller coaster. So very recommend. Yeah, see, they are heavy stories. I'm sure I have already recommended Hail Mary, but I'm rereading Hail Mary because I like it. By Andy Weir. There we go. Project Hail Mary, is it? No. Oh. I have the book right in front of me, and because the word project is super small, I think it's just called Hail Mary. Wait, you can't see it, it's behind me. Anyway, yeah, the word project is super small. Yeah, so if you want to read Hail Mary, beautiful, beautiful scientific story. No way are they making it a movie. Oh my god, I'm gonna die. My favorite part about it is that it has no. It technically, I don't think it has a romance, which is my favorite part about it. I mean, obviously the book is great, but selling point for me would be it's not about romance. I guess Red Rising can also be seen as it's not about romance. What is happening? How do you write the word rising? Okay. Yeah. Okay. Let's go back to the lecture because we got distracted. No way. Okay, so
we extract features. The exact way I'm extracting features is basically splitting the words using the Python split function and then counting the number of times each word exists.
Oh, okay. So we're splitting the words using space.
We then run the classifier. So actually, running the classifier is exactly the same as what we did for the rule-based system. It's just that we have feature vectors instead. And then if the predicted value is not value, then for each of the features in the feature space, we upweight the weight by the vector size, by the amount of the vector if y is positive, and we downweight the vector by the size of the vector if y is negative.
Okay.
So this is really, really simple. It's probably the simplest possible algorithm for.
You only raise oh my god, that's so true. I only like romance and K-dramas because no, I will respond. Because it's so not real and so fantastical and like very childish. I mean, I'm not saying I like childish romance. One of the series that I actually liked that had two consenting adults is Descendants of the Sun. Like, they're not chasing each other, they're not being stupid. But yeah, like 2 new episodes of Sonje Opkotyo, Lovely Runner, has come out, and I haven't seen it, and I am worrying about that. And yeah, that's a messed up series because of time travel. Yeah. Yeah. Actually, I was telling someone very recently that I really like tragic stories because then you feel like the potential of the what could happen is far more romantic than if it actually becomes true and they are human and humans are harsh and there's absolutely no happily ever after. So I'd rather have something bad happen to the romance in movies and TV series, not in real life, because then you'll be like, ugh, it could have happened. But if it actually happens, then it becomes a human story of just hurt, people hurting each other. Fun! Real life is fun. Right? Anyway, extracting features, right?
Training one of these models. But I have an example in this that you can also take a look at. Here's a training the bag of words classifier. And we can step through. This is on exactly the same data set as I did before. We're training on the training set and evaluating on the dev set.
By the way, all of this code is available on the website that I put somewhere. I can pin that. I can pin that. It's on his GitHub, and you just go here, and that's the rule-based, and that's the bag of words.
I also have some extra stuff, like I'm shuffling the order of the data IDs, which is really important if you're doing this sort of incremental algorithm, because what if your training data set was ordered in this way, where you have all of the positive labels on top, and then you have.
Huh? You're saying hi to who?
All of the negative labels on the bottom. If you do something like this, it would see only negative labels at the end of training, and you might have problems because your model would only predict negative.
Sorry.
So we also
on
shuffle
YouTube.
data, and then step through. We run.
I was looking at Oh, hello. What is a rule-based classifier? I will get back to you after I say hello to the other person on. I was like, how can you tell someone is silent? It's because it's their name. Sorry about that. Hi. Kind of off topic. Do you have a Discord server for this channel? No. Should I make one? I could. Do I know how to make a Discord server? Maybe. If it's can be done. Also to answer CR Ghost 7. What's a rule-based classifier? Very, very good question. Let's see if I can try and explain. explain. So this is the lectures from this this here. So we should watch your Twitter, maybe possibility of coming. Either Twitter or YouTube community. I could put it there as well. Sure, if you find it, presuming you will announce it there. Sure. I don't mind. Because it can be a protected space, even if it's public. It can be a protected space. So about rule-based systems, they are systems that, like in the simplest term, you write rules for the output that you want. Let's say a traffic light. That's a rule-based system, isn't it? If it's red, you stop. If it's yellow, you speed up. And if it's green, you go. So that's a rule-based system. Twitter, link in the YouTube doobly-doo. Yes, we do have the link for Twitter in the doobly-doos. And I think I also have the socials. I forgot. Oh yeah, okay. Context in NLP. Good question. So in this lecture, the guy creates a program. Like we can just go and look at this program that he creates. Rule-based sentiment classifier, and look at how like rule-based it is. It says we have a list of good words: love, good, nice, great, enjoy, enjoyed. Look at how even like enjoy and enjoyed, like that could have been contained instead of equals, but and then we have bad words: hate, bad, terrible, disappointing, sad, lost, angry. And then what you do is you say, if you find this word in the paragraph or sentence, that this is about checking movie reviews. So if those words exist, you count the good words or the bad words, and if there are more good words or bad words, we have some weight. Yeah, I think rule-based is like an expert system where the rule, yes, you have to write the rules yourself. Even like something like spell checking, some languages have rules. Let's say, let's take English as an example and say, if there's an S at the end, then that's plural. If you see the, or if you see a, then you know if it's, God, I don't know grammar words. You know, I think you understand what I'm saying. But like you have to define every rule for the model to understand the things. Yeah, it's old-fashioned AI basically, and not machine learning because it's not learning anything. Yeah, I suggest you go back and watch this lecture to understand what the Graham is teaching. I can put it in the chat so that if you are interested, you can go to this lecture that we are looking at, which is the first lecture. There. Yeah. It's our, oh, I mean, yeah. Like when a microwave oven says it has AI, it's often an expert system. Expert systems is also a thing that is, yeah. What would be the opposite of a rule-based system? Good question. I guess just normal machine learning. I wouldn't call it an opposite because even sometimes some of them have some sort of like intervention in a way. Is that a good word to use? Like human has intervened and has added some rules. Like I'm guessing up until like I don't know 5 years ago, Grammarly probably had some human touch because grammar has a lot of rules, but also it has a lot of not rules, that things that don't follow rules. So yeah, I hope that makes some sort of sense. Does it make any sense? key. So thank you. You are very, very welcome. Self-supervised machine learning. Okay. All right. So my time is running out. I have 5 minutes left, and I don't think I can finish this lecture. Let's quickly see where he goes with this. Okay. I think we'll just look at this code first.
The classifier, and I'm going to run 5 epochs of training through the data set very fast, and calculate our accuracy. And this got 75% accuracy on the training data set and 56% accuracy on the dev data set. So
not good at all.
If you remember, our rule-based classifier had 42 accuracy. And
so it's an improvement.
Now our training-based classifier has 56 accuracy, but it's overfitting heavily to the training set. So basically, this is a pretty strong advertisement for why we should be using machine learning. You know, the amount of code that we had for this machine learning model is basically very similar. It's not
machine learning model trained only on raw data without human labels. Hi, Ratnshwa? Hi. What I was about to say is self-supervised or unsupervised, right? Is self-supervised, does it mean unsupervised, or is there like a difference? If you can answer that, I'd be grateful, or I can Google it.
Not using any external libraries, but we're getting better at this.
Actually, I don't know if Google can answer. Sometimes you're like, do I Google this or do I ask ChatGPT? Because I don't know. Anyway. Cool.
So cool. Any questions here? And so I'm going to talk about the connection between this algorithm and neural networks in the next class, because this actually is using a very similar training algorithm to what we use in neural networks with some particular assumptions. Cool. So what's missing in Bag of Words?
Yeah, seems better than chance, but not by much. No, actually, yeah, you're right. Could be chance. He also said that there was overfitting in the training part. So yes, this is the end. All right. It sounds like rule-based did worse. Yeah. Oh yeah, because there were words, you know, like there were words that were not in the. You can make rule-based so good if you put everything in there, but that is really, really time-consuming and resource-intensive. Thank you, Cut. Thank you for coming back. Oh no, yeah, I have a timer. Yes, I'm using my phone. Thank you for coming by. I have missed your I mean, I enjoy having you here, and not only for the explanations that you provide, and those are very much appreciated. Sure. Maybe I can make a sprint. That is a cool. Oh my god, you don't have to. Huh. That's so smart. I mean, if it's possible, yes. Because I think the audio was horrible. With the not being normalized. It can be done manually, but it's long. I mean, I'm saying me, because I can do it on probably Audacity or something. That if you can do that, I'd appreciate it, but you don't have to spend your time, okay? Like, I give you permission, but don't waste your time, is the part of the permission that I'm trying to give. Alright. Today was really fun, thank you, even though learning about the transformers was fun, and I had a hard time because I had to concentrate, something I'm not great at. If all goes well, each time I'm like, if all goes well, I'll come back tomorrow. Tomorrow's Thursday, should be fine. Yeah, my time, I started half an hour later than I wanted to, but it is all right. Does animation, it does track my head, yes. Like I can turn around, but it doesn't do hand, and it's not animation, it's an app. Like it's an app that you can use right now, on whatever thing you use. Yes. It has some hand movements that one can use. I'm trying to find one. Oh, there we go. Okay. Yes, it's a mobile app called ZEPETO or something. It's a Korean app, but it's all in English, don't worry. It's really fun. And it can track your... You could probably make really cool stuff out of it if you edit it, and it has like video style stuff. For example, I don't know what's going to happen, but I'm going to try to run this animation of... what's happening? Yeah. It's just hand movements, nothing serious. Cool? Alright. But... Alright. Anyway, thank you for stopping by. I will go now. If I make a Discord channel server thing, I will let you know either today or tomorrow. Thank you. Really appreciate it. You don't, because like you can just take the courses on your own. You don't have to come and watch the streams. So I appreciate that. And like the fact that my channel has been gaining subscribers on YouTube, I'm like, why? And thank you. Anyway, thanks for passing by. I'm going to end the stream starting from 5. So if you have any other comments or notes, thanks for that part. Otherwise, I will go. Inshallah, see you tomorrow. Okay, ending the stream in 5, 4, 3, 2, and 1. Thanks.